So, Chapter 9 is the standardized mean difference. And this is a tool for expressing size of association, where the independent variable is a dichotomous categorical variable, and where the dependent variable is at the interval ratio level of measurement. In other words, the dependent variable is a numeric one. We have seen that to assess size of association between two categorical variables, the primary thing that one does is compare percentages, and the difference of percentages was our key measure perhaps there. And for examining size of association for two numeric variables, Pearson's R is a workhorse tool. So in our final sort of combination, we're looking now at one categorical variable and one numeric variable. And in particular, standardized mean difference is going to be used for a dichotomous two-category categorical. What the standardized mean difference is, it is a difference in means expressed in standard deviations. So if you look at this example here, we could ask the question, are group membership and self-esteem associated? And indeed they are. Basically, when one variable is categorical and the other is numeric, and we're going to assume that the numeric variable is the dependent one. Basically, one examines means to assess whether relationship is present. So if the means differ, there is relationship. If the means are equal in different groups or different categories, then there's an absence of association. So here we have a difference in means, and therefore we have relationship. Now do recall, we're not saying anything here about whether this relationship is statistically significant, that is, unlikely to be due to chance, and further, we're not talking at all about cause of relationship. We're just examining in one sample, is there relationship? And here our means differ, and therefore there is. How large is the association between group A or B and self-esteem score? In other words, does a difference of 5 self-esteem points, which is to say 45 as a mean versus 40 as a mean, does this represent a large difference, a medium one, or a small one? The units of the self-esteem scale are arbitrary and intangible. Therefore, there's no way to assess size of association. Now let's go ahead and add information on the standard deviation. So the information added here is that the standard deviation in each of our two groups is 10. Now let's ask the question, how large is the relationship? Or we can equally say, how large is the difference in means between group A and group B? Straightforward way to answer this question is to express the difference in means in standard deviation units. And this is what a standardized mean difference is. So the standardized mean difference conveys the number of standard deviation units by which the means of two groups differ. Here's our formula for the standardized mean difference. So this symbol here conveys mean in group 1. We're going to arbitrarily designate one group to be group 1 and the second to be group 2. Here's the mean of group 2. Here's the standard deviation. And more particularly, this is the standard deviation within groups. We are going to presume equal standard deviations in the two groups. So we are going to presume that the standard deviation in the first group equals that in the second group, and that that is the value of the standard deviation within groups. So for instance, on the prior slide, the standard deviation in each group was 10, and so therefore the standard deviation within groups was 10. Now I'll just say that in real world there are modestly more complicated formulas that compute the standardized mean difference in situations where groups differ by some. It is often the case that standard deviations are quite similar in two groups. So though our way of simplifying the formula isn't fully realistic, it gives us a very good approximation, a very good estimate of the standardized mean difference. The book has notations of more accurate formulas that you can use should you desire and need a precise method for calculation, for instance, for a report. So here's our formula, and here's our calculation of the standardized mean difference. The mean in the first group, 45, minus that in the second, 40, divided by the standard deviation within groups, computes to 0.50, which is to say that the mean self-esteem score in group A is 1/2 of a standard deviation then higher than is that in group B. And here's a second example. Those in group A lose an average of 50 pounds. Those in group B lose an average of 20 pounds. The standard deviation in each group is 10 pounds, and here is a calculation of the standardized mean difference. 50 minus 20 divided by 10 equals 3. The mean weight loss in group A exceeds that in group B by 3 standard deviations. Here are some qualitative descriptors of size of association for the standardized mean difference. So basically, if you see an SMD that's smaller than about 0.20, and I should be more precise and say whose absolute value is less than 0.20, because the standardized mean difference can compute to a negative. But if that absolute value is less than about 0.20, then the relationship is starting to be so small that it's almost, well, it's just quite small, and at some point you say to yourself, practically speaking, the relationship is so small that it's nearly the absence of relationship. And then the other end of the continuum, if the absolute value gets to be greater than about 1.3, you have a relationship that is very large in the context of social science. Clearly you can see that differences of about 1 standard deviation, which is to say an SMD whose absolute value is greater than 1, that's a kind of a good yardstick for you're seeing that a relationship is really quite large. I mean, obviously a value of 1 is interim between these two values. This slide presents graphically standardized mean differences that correspond to the 4 sizes depicted in the prior slide. So here is a figure in which the mean of the larger group exceeds that of the smaller group by 2/10 of a standard deviation. So in all of these figures, in all 4 of these figures here, I mean, we're presuming that the shape of the distribution is normal, and we're presuming that the spread of each distribution is the same. But I note that the standardized mean difference doesn't require that the distributions be normally distributed. I mean, we've done that here for convenience. It's a good measure even when you don't have two normal distributions. But you see here that where the difference is 2 standard deviations, there's a great deal of overlap between the two groups. So that another way to say this is that many people in the group with the lower mean have higher scores than many of the persons in the group with a higher mean. But if we jump down to the lower right corner, now we're seeing graphical depiction of a difference of 1.3 standard deviations. So we've got here what would be categorized as very large association, and now you can see that the distributions are much more distinct. There's much less overlap. There's a much stronger delineation between the two distributions. And so that's the idea here. As the absolute value of the standardized mean difference increases, the overlap decreases and the distributions become more separate and more distinct. And look even at the very strong association here as conveyed in the lower right figure. Though the groups are quite distinct here, you can see that there's still some overlap, so that when we say that the distribution is very large, we're speaking in the context of social science rather than strictly in a mathematical way. In what would perhaps be conceptualized as a perfect distribution or the strongest possible association, there'd be absolutely no overlap between the groups, but you just wouldn't find a difference that large in social science research. There's a particular situation in which the SMD is not a good measure. Now I did mention that the shape of distribution is not important, that you don't need to have normal distributions in order to calculate the SMD and to meaningfully use its descriptors. But the SMD is not a good measure, and particularly the descriptors should not be used when standard deviations differ substantially. I think the text says when one standard deviation is more than about a third larger than the other, that it's not a good measure. But take a look at this data here, and you've got this difference of 5 points. The problem here is that the standard deviations differ considerably in the two groups. So then the question comes, well, which standard deviation would one use in the calculation? So if we would choose to use the top standard deviation, our SMD would calculate to 0.5. Whereas if we chose to use the bottom standard deviation in the formula, it would calculate to 0.25, a very different value. So, this is just a caution to say that the SMD is not a good measure when the standard deviation differs greatly in the two groups. And as I've already mentioned, as presented here, the SMD is an approximation. It's an informal measure where we presume the standard deviations to be equal. So when you need precision for the SMD, Cohen's D or Hedges G are good ways to figure out the SMD. And the footnotes of Chapter 9 have the formula for Cohen's D, and you can find Hedges G easily online. Now, one straightforward way to calculate the SMD is as we have done, which is to presume that the standard deviation is equal in the two groups. Now, another way to do so, and a measure that is often used in experimental designs, that is, designs that are attempting to look at the effect of an intervention, I've termed effect size for means. So the difference between effect size for means and the SMD as calculated earlier is in the denominator. So what's used in the denominator for effect size for means is the standard deviation in the control group. If there are two groups, the control group is the group that does not get the intervention whereas the experimental group is the group that does get the intervention. I won't present a calculation example here, but again, the key thing is to divide by the standard deviation in the control group. Now, a measure that we will simply mention and not go into too much is eta squared. Eta squared can be interpreted as the proportion of variance in a numeric variable that is explained by a categorical variable. That your computer software programs can compute eta squared, and it's an excellent measure of size of association when you have 3 or more groups. I guess I should repeat it before going on. When I say it's an excellent measure of size of association, I could equally well have said it's an excellent measure of effect size. The term effect size is really a synonym for size of association and strength of association. Effect size often gets used when we talk about experimental data. So here are guidelines for interpreting the size of association for given values of eta squared. So this concludes our study of measures of size of association between two variables. And the next section of the book is a short one and deals with the assessment of causality.